A transfer curve can be a useful tool when determining what amplifier is appropriate for a given application. So what our transfer curve shows us is the output power versus the input power for a given amplifier. So let's go ahead and set up a basic plot here, and then we'll describe some items on this plot as we sort of add them in. So we're plotting our output power versus our input power. And so typically our output and input power for these types of plots are going to be expressed in dBm, which is decibel milliwatts. And so our decibel milliwatts is calculated very similarly to how we calculate our power or a voltage or a current in decibels. So we have dBm is equal to 10 log base 10 of our power in watts divided by 1 milliwatt. And so the main difference between this decibel milliwatt and a normal decibel is here we have an actual fixed reference point of 1 milliwatt as opposed to just some arbitrary decibel unit. So we can come up here and say this is typically in decibel milliwatts and decibel milliwatts. Okay, so a couple of things we want to point out about sort of key characteristics of this transfer curve. So oftentimes we're going to have some input power that has to be exceeded before all of our devices are turned on. And so that's true of, for instance, the amplifier we looked at in the previous video. So let's just say some input power must be exceeded for all devices to turn on. And so what that means is maybe for small values of input power, we're not going to have any output power to turn on. And so if we come up here, we can start drawing our plot. Let's say, sort of to make this a little more clear, let's say we have, here's our 0 input point, here is our 0 output power. And so maybe what we have is something like this. So right at this point, we're not turning on because we have to use some of that input power to turn on the devices. So maybe somewhere over here, some positive input power is where we start to get some output. So once we have enough power to turn it on, we're going to have a range where it's approximately linear. So we'll have something that maybe looks like this. And so this is going to be our, what we call our input dynamic region. So let's come down here and describe that in words, and then we'll come back and plot a little more. So this is our device will have a useful dynamic range. So a device has useful dynamic range, and that's that linear region. And then after we sort of get to the end of this linear range, what we're going to see is we're going to have some saturation effects. So after we get saturation, so coming back up to our curve here, so we're roughly linear here, and then at some point what's going to happen is if we keep on trying to put more input power, we're kind of going to be rolling off and we're not going to be linear anymore, and we're going to have some more complex relationship. So a couple things that we can define on here right away. So let's go ahead and say we have this right here. So this region where it's linear is going to be our input, change this back to the solid line. So this is going to be our input dynamic region. And so in most cases, we're going to want our amplifier to behave linearly. So we can sort of, knowing this, we can limit our input powers to be within this range. So I've not put any numbers here, but for instance, maybe this is around 5 dBm, and maybe this is around 30 dBm. So maybe we need to keep our input power in that range. And so again, that's so that remains linear. So another sort of key metric that we can note here is we can extend this linear region. So we can say, well, this had some linear approximation, And if we extend this, so let me label this here as our linear approximation. There's sort of a key point called our 1 dB compression. And what our 1 dB compression is where we have dropped 1 decibel from this linear approximation on our actual saturated output. So let's say, let's do pink, hopefully that'll stand out. So let's say the difference between our actual power here and what it would have been based on this linear approximation is 1 decibel. Then this is our 1 decibel compression point. And so what that is again just when our output has dropped 1 decibel below. So 1 dB compression is where we've dropped 1 dB compared to the linear approximation. And so that was a linear approximation for that input dynamic region. So again, this kind of graph can be useful in terms of telling us what type of amplifier we need to look for, and then once we have it, we can know what we need to keep our input powers between in order to stay in that input dynamic region. And we can also, of course, correlate these to certain output powers as well.